Yes.
Yeah,
So
thanks.
to give a brief introduction about CSIR, it's a Council of Scientific and Industrial Research, and it's a national central government organization which has labs which are working in the different areas of science and engineering, and they're spread across all over India. So where I'm coming from is CSIR Structural Engineering Research Center, and we are located in Chennai, and we basically deal with the structural engineering domain. There are four different areas in which we work. The first one is the basic and applied research, where we take up the R&D projects, which advances the science in the direction of structural engineering. And we also do some kind of industrial and industrial research and consultancy. So what are the problems that are faced by the industries? We try to address those issues by going on to the field visits and taking some measurements. We are also contributing towards the strategic sectors, and we deal with the nuclear power plant components as well as the defense projects. And also we work towards the society whenever the need arises, such like in the case of COVID-19, we work towards the establishment of hospital units. So the lab where I come from is Advanced Seismic Testing and Research Lab. So this lab was established in 2007 in CSIR SERC, and we have the state-of-the-art facilities which comprises of two shake tables which can be run in conjunction with each other, so that we can test the structures which span across um, multiple lengths, which are extended payload. And also we have a pseudodynamic test facility where we can do multi-support excitation as well as we can test some of the critical structures which are very tall in nature. So the focal point of our lab is earthquake engineering and as well as the vibration dynamics. So some of the some research projects that we have taken up are in the area of structural dynamics, seismic performance evaluation of civil structures, and advanced response control strategies for civil structures, and seismic resistant design. So coming to this presentation, so this is how I have divided this today's talk. So we'll start off with some introduction, and the whole talk is divided into three parts. The first part will focus on various type of dynamic testing methods. We will see what are the conventional methods and how these methods have advanced to the current dynamic testing methods, where we are able to solve some complex engineering problems in structural dynamics. The second part of my talk is going to focus on the vibration control strategies. So here I'll just give an overview of what are the different categories of vibration control strategies and how they are adapted for civil structures. And in the part three, I will focus more on the application part, where I will try to highlight some of the projects that we have taken up in the domain of dynamic testing and also vibration control, followed by conclusions and some future directions. Yeah. So coming to the first part, we will see the various dynamic testing methods. So first of all, before we go into the different dynamic testing methods, it's very important to understand why we actually need to go for the dynamic testing. So we all know that most of the structures around us are made up of concrete, and concrete is a very heterogeneous material. And it becomes very difficult to predict the nature of the concrete, how it is going to behave when some extreme loads are acting on it. Because of which it becomes very difficult to model the response of a concrete structure. So the only way left for us is to go for the experiments, because that's the ground truth. Then we also see nowadays people are coming up with aesthetically pleasing architectures which are of complex shape in nature. And when we have something which is as complex as that, it becomes very difficult to accurately model that kind of a structure. So in such cases, experiment remains as the only way to get the actual response. And even though we have various computational models, we will be knowing that in various software, we have some independent models in Abacus and ANSYS and Athena. But these models have been developed based on the experimental results that have been carried out over the over the previous experiments, previous decades. So based on the experimental results, only these models have been developed and they have been fine-tuned for their performance. And also, let's say we come up with some new kind of a material or some, nowadays we are using some advanced cementitious composites for which the conventional model may not be suitable, or we need to slightly modify those models in order to make them applicable to new kind of composite systems. So in such case also, we have to go for the experiments, and then only we can tune these models to accurately predict their dynamic behavior. So last but not the least, we also know that most of the coding recommendations that we currently have, they are also the basis for them is also the experimental results. So let's look at some of the conventional dynamic testing methods. So once when we come to the dynamic testing method, they can be categorized into two parts. First is called as the open loop dynamic testing methods, and the second one is a closed loop dynamic testing method. So what happens in open loop dynamic testing method is that we apply some force or displacement onto the structure, and we do not measure any response. I mean, we do not measure the response to decide what is going to be our next force or displacement that is going to act on the structure, which means we are not taking any feedback from the structure. So all the displacement and forces are predetermined, and we directly apply onto the structure. There is another category of dynamic testing method, which is called as the closed loop testing method. So in these testing methods, what we do is we apply some force or displacement onto the structure. We measure the response of the structure, and then we decide what is going to be our next course of action, which means we are taking the feedback from the structure, and we are trying to see how our structure is reacting to that force. And then only we are deciding what should be our next time step force or displacement. So coming to the different dynamic testing methods that we have in our lab are shown here. We can either go for the quasi-static testing method, which is generally done at a sub-assemblage level or a component level, or we can go for a shape table testing method, or we can go for pseudodynamic testing method. So we will see these methods one by one and understand what are their advantages and disadvantages. So coming to the quasi-static testing method, what happens here is, so we just take a part of or component of a structure. We do not take the whole structure here, and we try to apply some kind of a cyclic load in terms of displacement at a very slow rate. So when you apply force or the displacement at a very slow rate, what happens that your dynamic equation has three components. One is the inertial component. The second one is the restoring force due to stiffness, which depends upon your displacement. And then we have damping, which depends upon the velocity. Since you are conducting your test at a slower rate, you are not able to apply the acceleration and the velocities, due to which your inertial and the rate dependent effects due to the damping are not accounted. So this kind of testing is usually used to study the hierarchy of collapse or to understand the hysteretic or a cyclic behavior of a particular component. So in this video, I'll just show you sub-assemblage that we tested here. So here, this is a bridge bend which is being tested, and it is given the cyclic load in order to understand the hysteretic behavior of a component. So here you'll see that we are not testing the whole structure, but only a part of it. And then we try to get the hysteretic component, and we use that information to model a behavior of the whole structure. So since the testing is carried out at a very slow rate, we are not accounting for the inertial and damping contribution that comes from this sub-assemblage. So the next one we have is called as the shake table testing. So as the name suggests, so we put a structure on a table which is kind of shaking. So what we try to do here is we try to replicate the ground motion that a structure would experience in a time at an event of an earthquake. So we get the time history, and then we try to earthquake time history we try to simulate using this table. So this is also an open loop testing method because we already know the acceleration level, that ground acceleration level for a particular earthquake. So all these are predetermined. So we are not measuring any response from the structure to decide what is our next action. And since this test is carried out at the actual rate, the inertial and the rate dependent effects that comes because of the structure are accounted. So one of the major disadvantages of this method is that most of the shake tables that we have some physical limitations. So these limitations are generally in terms of the weight of the structure that they can support. And when we go for the real structure testing, most of the structure needs to be scaled down for shake table testing. So when you scale down a particular structure, one of the problem becomes is some of the local phenomena such as crack pattern and the local buckling. You may not be able to capture that accurately once you scale down the structure. So if you want to understand the global response of a structure, then you can go for a shake table testing. But if you want to focus on some of the local phenomena, that you may not be able to replicate using shake table testing. So Here I'm showing you some of the shake table testing that we have carried out in our lab. So here in the first video, we are testing a non-structural component, which is a cable tray and AC duct units and some panels, wall panels. So whenever we get some new component that has to be qualified for a particular zone, and we do the testing for that particular zone and see whether the response are within the permissible range. So in the second video, what we have here is a nuclear power plant components. It's a valve. So these nuclear power plant comes under a critical facility, and we have to ensure their proper functioning even at the time of an earthquake. So here, our main objective was to subject that particular valve to a site-specific earthquake and check whether it's gonna be functioning at the event of an extreme earthquake or not, in order to ensure that the plant is going to remain safe even when it is struck by an extreme earthquake. So the next that we have is called as the pseudo-dynamic testing method. So as the name suggests, it's not really dynamic testing, but it's a pseudo-dynamic testing method. So what we do here is very similar to how we idealize our dynamic equation when we solve it for a ground excitation. So instead of making a base which is moving, what we do is we fix our structure onto the rigid platform, and then at certain location we use actuators to apply the earthquake forces that will come onto a structure at an event of an earthquake. So this is a closed loop testing method, which means that this test takes the feedback from the structure and then decides what is going to be the next time step. And this test is usually carried out at an extended time scale. What it means is, if the earthquake actual time history is only for 1 minute, this test can go up to an hour. So at every time step, we find out what are the forces that are coming at this lump mass location, and then we use an actuator to apply those forces on the structure. Then we measure what is the force that was required and use it again in our numerical model, which accounts for the inertial and the damping characteristics of the structure, and find out what is the next time step. So one of the disadvantages of this particular testing method is it is only applicable to certain types of structures where you can idealize your whole structure in the form of a lumped mass model. The another disadvantage of this method is that the test is carried out at an extended time scale. So we are not really accounting for the inertial and damping forces. They are represented with the help of a numerical model. So here, one of the tests that we carried out in pseudo-dynamic testing method. So here you can see that we have a nuclear power plant component, which is a control rod assembly. So this control rod assembly has a function of absorbing the extra neutrons that are causing the fission reaction. So at an event of the earthquake, they have to ensure that this should function perfectly. So here you can see that we have this rod assembly, and at different locations, we have attached the actuator. And whatever earthquake forces that comes onto this assembly are applied with the help of actuator. Yep. So the next class of testing that we have here is effective force testing. So this is also very similar to your pseudo-dynamic testing method. So what we do here is we have a structure which is fixed onto the ground, and we all know the earthquake forces that a structure experiences is mass times acceleration. And then we use a series of actuators to apply those loads onto a structure. If we compare this method with the pseudo-dynamic testing method, we don't have any computer model here. So we try to do this test in real time, which means that the inertial and the damping characteristics are accounted from the structure directly. And this is also an open loop testing method, while pseudo-dynamic testing method is a closed loop testing method. The disadvantage of this method is that this is also limited to the structure with the fixed base, and which can be approximated using lump masses. And the other thing is you have to operate your actuators in the force control mode. So the force control of an actuator is a tricky situation, because displacement control, you have a PID to do that. But once you go for the force control, you are attaching your actuator to a structure whose properties you are not very sure of. So the actuator does not know how much it needs to move in order to achieve that force. So the force control becomes a tricky issue when we go for effective force testing. So in order to summarize these different testing methods, we have the quasi-static testing method, which the inertia and the rate dependent effects are not captured and only a component is tested. In shake table testing, we have to use a scaled down model of a structure which does not capture the local phenomena such as local buckling in the clad pattern. In pseudodynamic testing, the test is carried out at an extended time scale due to which we do not account for the inertial and rate dependent effect. Effective force testing method we have to do for the force control, which becomes difficult for achieving when we attach to a structure about which we do not have good idea about its properties. And the another disadvantage of pseudodynamic testing method and EFT is that they're limited to structure which can be idealized as a series of lump mass. So you can see that all these conventional testing methods that we have been using for quite some time, each of these methods has certain kind of disadvantage, and they are limited to only particular type of structure. So their usage should be very carefully done because you have whatever approximation you are making to find the dynamic response of the structure, that should be valid for that particular structure that you are testing and what response you are looking at. So in order to overcome these disadvantages of conventional testing method, a new kind of testing methods have evolved over the last couple of decades, and that is called as the hybrid testing. So what happens in hybrid testing is, let's say I have a structure, it's a base isolated structure, and let's say I want to get the response of this structure. So what I do is I partition into two groups, two substructures. The first part is, let's say, the building. I call it as the virtual substructure. And we try to, since we have a decent idea about how a building is modeled, we can represent it using a computer model. And let's say I have a highly nonlinear system, which is represented by a base isolation, and I do not have good idea about the modeling of that or how it's going to behave during earthquake. So what I do is I actually physically test that. And now what I do is, we know that we have separated these two substructures. So there's going to be an interface interaction between these two structures. And that interface interaction is accounted using a transfer system, which can be either a shake table or an actuator. So this is how it looks like. So we solve a numerical substructure. We find out how much displacement or force that needs to be applied at the interface. We use an actuator to apply that. Then we measure how much force or displacement was required for that. And then we again feed it back to a computer model. So you can see that just by testing only a part of a structure, we try to get the response of the complete building. So you can actually view this as an experimental finite element. So just like in finite element, you have interface boundary condition continuity equation. The same thing we are trying to achieve in the physical world. So your base isolation can be seen as an experimental finite element that you have taken out from your model, and whatever is the interface boundary condition between these two substructures that you are trying to realize with the help of an actuator. Right. So it's basically based on the concept of structural partitioning. So here, let's just see if I have a 2 degree of freedom system and I'm having a base motion and I want to find the response of the system using hybrid testing. What I can do is I can partition it into 2 parts. So here you can see the governing equation and the interaction between them. So the reaction forces that comes is the feedback force that is shown here. And if I have to go for the hybrid testing, what I can do is I can have the mass 2 as my computational model and the base excitation. And I find what is the displacement of this mass 2 in the presence of the feedback force that comes from my mass 1. And then I try to drive my actuator in order to ensure that actuator applies the same displacement x1 as a mass m2 will experience when there is a base motion. So just by testing a single degree of freedom system, which is shown by m1, we can actually get the response of complete 2 degree of freedom system. So let's look at the control loop. So as I said that we have 2 substructures here, which are shown here as virtual substructure and the physical substructure. And the external input can be in forms of the wind forces. So if I have a wind force, it can act onto my virtual substructure. We can also have some forces that act directly onto a physical substructure, for example, an earthquake. And then we have the boundary condition and the work conjugate boundary. So, but when we go for RTHs, which is real-time hybrid simulation, which is another name for hybrid testing, what we have is we introduce some extra things into our system. Like I said, in order to realize the boundary condition, we have an actuator, which is called as the transfer system. We also have a sensor which takes the feedback and feed it back to our computer model. So your actuator has internal feedback mechanism that also becomes a part of this control loop. And since the actuator is attached to my physical substructure, they are also going to interact with each other. Because you know that Newton's third law says that for every action, there is equal and opposite reaction. So when my actuator is trying to push my physical substructure, it is also going to apply some force onto my actuator. So that natural feedback is called as a natural physical feedback. So you will see that in order to solve a very simple problem, which looks something like this, we have complicated that by introducing some extra things into the system, which were not really a part of that. So when we design controls for the actuator to do hybrid testing, we have to account for all these new dynamics that have been introduced into the system. So here I've just summarized the different forms of cyber physical testing. So first side, we have the pseudo-dynamic testing, where we account for our inertial and damping characteristics in the computer model. Then the second, we have the real-time hybrid simulation. In real-time hybrid simulation, we take one part of the structure itself in the computer model. In the pseudo-dynamic testing, we had only stiffness and damping, but here a subcomponent itself is modeled in the computer. And then we have the real-time substructure pseudo-dynamic testing, where we take into account only the stiffness and damping from the physical part that we are testing and account the dynamics of the component and inertial and damping effect of the remaining structure also in the computer model. And then you have the substructure PSD, where the inertial effects and everything is accounted in the computer model. So these are the different forms in which you can do the cyber physical testing. It's also called as cyber physical testing because we have one part which is being represented in the computer while the other is physically tested. So you can see that just to get the structure whose response we want to evaluate is called as the evaluated structure, which is shown in the center. So we can evaluate the response of the structure using different methods based on the amount of information that we have for that structure. So here I'd just like to show you a small video of how exactly hybrid simulation works for a complex case. Let's say in the case of a building. I'll just play this. So here you can see that we have this whole building and which comprises of, let's say I just take out one column, which is the physical column, and that alone is tested in the lab. So you'll see that we need a special kind of reaction frame in order to apply all the boundary conditions that come on the column, which can be in the form of displacement and moments. So here you can see the finite element model of the whole building, and we are taking out a physical finite element, which is actually tested. And here they're showing the different boundary conditions on this column. So now they have a different force transfer mechanism, which comprises of 8 actuators. And this system is able to apply all these interface boundary condition onto my physical specimen. So you'll see that just by testing this one particular component, we can get the response of the complete building. Now you will question that why we are testing only the one component. It can be some part of the structure that you have done some kind of retrofitting and you want to evaluate the performance of that strategy, or it's some kind of column where you have used some kind of composite material. So you want to test that part alone, how it behaves in a structure. So you will see that another advantage of this particular method is that if I want to test the behavior of this component in different structures, all I need to do is simply replace the computer model. So that becomes, it saves a lot of time because we don't have to wait for the construction of the specimen. And also it becomes very economical. So all the parametric studies, if you want to do for a particular component, that can be carried out in a very economical way if you go for hybrid simulation. So let's look at some of the application of hybrid simulation. So here I'm showing the case of, let's say I have a soil foundation structure interaction. So we all know that soil is a very complex system and it has got a distributed mass. We do have some of the soil models such as Winkler models and all, but that is very, in that we approximate the soil behavior using a series of springs and all. That may not be much accurate. Or let's say you have come up with a new model for defining the behavior of a soil under different condition, and you would like to validate that. So what we do is we test the soil in a laminar box here, And in order to represent the dynamics of the superstructure, we use a Stewart platform kind of a thing. So we need to operate this Stewart platform in such a way that it applies the same reaction force onto my foundation system as it would experience if some building was resting on top of it. So the similar kind of experiment was carried out in University at Buffalo. This was a PhD work of Stefanovi, uh, Katharina Stefanovi. So here you can see that we have a very huge laminar box, and this they filled up with the soil and all the necessary sensors to measure the pressure. They wanted to see the behavior of a saturated soil. So here you can see that they are filling up the laminar box with the sand. And after that, they do all the piling process in order to represent the foundation. So here now they have put the piles in the placement, and these are the pile driving mechanism. So they are driving the pile into the soil now. And once the foundation is ready, they put an active mass driver, which is in a form of a shaker. So you will see that this shaker is operated in a way such that it will replicate the dynamics of a particular building. So just by using this shaker alone, we can actually get the response of a soil foundation structure system for different buildings just by replacing the computer model. So here you can see the advantage of using such kind of testing method. This may not be possible with any of the conventional testing techniques that we have, because the size of the structure is so huge. And if you scale it down, you may not observe the same behavior in the soil as you would observe in this particular case. So another application of RTHS is when you have a problem which actually spans multiple domains. So here I'm showing you a system which comprises of a floating offshore wind turbine. So here you have the first part of the turbine is the wind turbine itself, which is subjected to aerodynamic loads. And then we also have the floating platform, which is subjected to hydrodynamic loads. So you will see that it has both wind load as well as wave loads. And in order to do such kind of testing physically becomes a very challenging task. So such kind of testing we can do using hybrid testing. So in hybrid simulation, what we do is we just take the turbine part alone, and this alone is tested in the wind tunnel. And then the dynamics of the platform and the hydrodynamic forces are represented using a computer model. And then we have an actuating mechanism, which is shown here. You can see that the simulated wind profile is applied directly onto my wind turbine using wind tunnel, while the base motion or the floating platform motion is simulated using an actuator assembly. So you can see that this type of hybrid testing is able to deal with the problems which spans across multiple domains, and for which you may not have readily available testing facility. So to get the response of such kind of a system, we can utilize hybrid testing. So here is one case where of floating offshore wind turbine, which is shown here. So this wind turbine is actually being tested in a wind tunnel, and we have a base assembly which is simulating the motion of the floating platform subjected to a particular wave condition. So you will see that without testing the whole structure in a wave basin, we can actually get the dynamic response of the floating offshore wind turbine. Now you can do the similar thing in the wave basin, where you have the aerodynamic part as a computer model and the turbine as a computer model, while the platform dynamics are simulated physically. So another application is the testing of a flexible bus conductor. So we all know that how critical the substation facilities are at a time of an earthquake, because we need to ensure that uninterrupted power supply, and we want the things to go back to normal as soon as possible. So it becomes very important to study the safety aspects of the substation equipment. Most of the substation equipment are often interconnected using a flexible conductor, the behavior of which is often not known and chaotic. So in order to find the response of this conductor when it is interconnected with two substation equipment, we can use hybrid testing. So here you can see that we have a flexible bus conductor which is connected to surge arrestor and transformer. Now, instead of testing directly the surge arrestor and transformer, we are using a tower assembly which is called as the equipment simulator. So each of the equipment simulator is trying to simulate the rocking behavior of surge arrestor and a transformer. And then we have the interconnected cable. So you will see that when the substation equipment, there are various kind of substation equipment, so we need not change our physical test when we are dealing with the response of a conductor dynamics. We can simply replace that in the computer model and find the response of this whole system. So here you can see one of the tests that was carried out during my postdoctoral studies. So here what we are trying to do is these slats can actually have a different impact onto the response of the whole system. So here you can see the two equipment simulators, their frequency and damping ratios are shown here. And for different slats, you can see the response of the conductor is different. And that is what we are trying to get experimentally. Now, this experimental data was carried out for different kinds of these conductors. And once we have enough data, we can actually work on developing computer model, which can give us the accurate response of the conductor. The other application of RTHS can be, let's say we have a base isolated spent fuel tank. So spent fuel tank is basically a facility where you store your spent fuel of a nuclear power plant. And it's usually stored into a pool where, and we have a stacking mechanism where the spent fuel is stored. So these multiple racks and this whole thing is usually base isolated in order to reduce the response that comes onto the spent fuel tank. And what we can do is here we can test the base isolated structure alone, while the whole tank assembly and the water effect can be accounted in the virtual substructure. So similarly, this method can also be used for various other testing methods. So we all know that we have different kind of seismic protection devices ranging from semi-active to the active passive devices. So MR damper is basically a semi-active device, which means that we can actually change the properties of the damper by applying a suitable magnetic field. And then we have elastomeric bearing, we have friction pendulum, elastoplastic damper, and tune mass damper. So all these, whatever seismic protection device that we develop, we have to ensure its performance for different kind of structures. So that can be carried out economically if we go for hybrid testing. So here are some of the examples. Let's say I have a base isolated structure and a building. This example was already shown in the first slide. So here we can test the base isolation system alone and get the response of the structure. Let's say I have a case of an MR damper and where I develop some kind of control mechanism. So such as MR damper is a semi-active device. For that, you need to design a controller. And in order to see how your control algorithm is working, you can actually use hybrid testing and just test that damper alone. And you can see the performance of the whole structure with your control algorithm using hybrid testing. Then it can also be used for studying the response of a bridge pier. Let's say here we have an example of a bridge which is resting on 2 piers, and we have a water flowing under that. So what we do is the deck we model as a numerical part, and the pier we test physically. So then we try to get the interaction between these groups of structure using the load transfer mechanism, which is shown origin, which applies the interface boundary condition in the terms of forces, in terms of displacement and rotation. So it can also be used to study the fluid soil structure interaction problem, where if a particular pier is subject to this bearing effect, that can be studied by just testing a pier alone in a loadless tank. It can also be used to study the behavior of your retaining wall. So we all know that retaining wall is subjected to the soil pressure, and this soil pressure can be applied here using a series of actuators. So if we have to carry out such kind of a test in the lab to find out whether the retaining wall that we have designed is stable or not, that can be carried out using hybrid testing. People have also tried to use it for extreme cases where you have an FE model of a building frame and all the wind forces and hurricane forces are applied using a series of actuators. And also it can be used to study the fluid debris structure interaction when you have a tsunami. So tsunami forces are usually very high, so it may not be, your testing will be limited by the capacity of your actuators. So it may not be a practical solution, but you can still get some response of a structure if you want to study for tsunami forces. So now let's come to the second part of the lecture, which basically focuses on the vibration control strategies. So We all know that vibrations are almost everywhere. So right from the building in which we stay to the car in which we travel, because of the road undulation, we get some vibration. It is also there in the machines that we use, the wind turbines, and even the space telescope, the things that we have outer space. So in space telescope, your telescope is supposed to aim at a particular star which is at a long distance, and even the micro vibrations can actually change the focus of your telescope from a particular star because you are focusing at very far distance. So you need to address those micro vibrations. So you will see like these are the different domains where the vibration occurs. And why do we need to control these vibrations? So first is because of the noise, it may cause some kind of a discomfort to the people around that particular source of vibration. The second is the vibration, especially in the structure, it might cause some discomfort to the residents. So, or the operator, if it's a machine. In order to reduce that effect, we have to go for a reduction in the vibration. And the third and the most important aspect why we have to reduce the vibration is it can lead to the fatigue and fracture of a particular component or the failure of a particular structure. So in order to reduce that and extend the lifespan of a structure, we need to address the issue of this vibration. So there are two kinds of vibration. One is a structural and another one is a mechanical vibration. So they differ slightly in the nature. Like if you go for space structure, they have a very low or natural frequency and the amplification is very high. Whereas in case of civil structures, the natural frequency is slightly on the higher side compared to your space structures. So the environmental disturbances in case of civil structures, which is in the form of wind and earthquake, that occurs for a wide range of frequencies and amplitude, and often they are unknown to us. While if we have to deal with the space structures or the mechanical structures, such as or even the machine vibration, the environmental disturbances that comes are usually deterministic, and we have a fairly good idea about the kind of disturbances the system is gonna experience. Civil structures have inherent damping and they are usually stable, and they may get destabilized if you use active control. But most of the aerospace structures uses some kind of an active stabilization. This is mainly possible because we have good information about the disturbances that are coming on the system. And also the performance specification in civil structures are pretty coarse in the form of like we just have need to reduce the peak amplitude or the motion time it takes for it to settle down. However, these restrictions can be quite strict in case of aerospace structures or mechanical structures. So the vibration control strategies can be divided into two parts. First part is called as the passive vibration control, and the second is called as the active vibration. So what happens in passive vibration control? What it means is it does not need any external stimuli for it to be active, which means that it does not need any external source of energy or actuation for making it work. So some of the example of the passive elements are base isolation system or viscous fluid dampers. So they have the inherent damping and they do not need any external stimuli. Whereas in case of active structures, what we have to do is we need to actuate that system in order to generate the opposite force which can damp these vibration. So one of the advantage of passive system is that they are very cheap to design and economical, and they're easy to maintain, and they cannot destabilize structure. Whereas the active structures, they work only for a particular band of frequency, and you need to design the controls for your structure. And sometimes if your controls are not designed appropriately, it can destabilize your structure. Passive structures really work for a small frequency band, and active structures, you can actually decide which frequency range you want to work with, and they are often very expensive to design. So here you can see a demo of an active car suspension. So here they use the MR dampers in order to reduce the effect of the road undulations that come on the car. So the Bose suspension one is the one having the active system for their active suspension system. So you can see that how the car body is shaking once it goes above these road undulations. Whereas once you go for an active suspension system, It changes its property in real time and reduces the motion that comes onto the car body, thereby increasing the comfort of the rider. So you can see here only the suspension part is moving while it tries to maintain the car body in the still position. So you can see these undulations are causing so much of disturbances. While when you have the Bose suspension system, it moves smoothly over those undulations without causing any discomfort. Right. So what are the different kind of vibration control devices that we use in structures? So most common one is the tune mass dampers that is used for bridges, buildings, and towers. We also have active systems in the form of active mass drivers and active tendon system that can be used for the bridges. And besides this, we have various kind of dampers that can be either active or semi-active or passive in nature, depending upon the viscous medium that is being used for these dampers to actuate. So here I've shown the classification of various type of vibration control methods. The passive one are the which does not need any controller or any kind of control system for the actuation. The semi-active is somewhere between your active system and the passive system. What it means is if you do not provide any external stimuli, they will behave as a passive system. Once you add your control system to the semi-active system, it will start behaving as an active system, and you can control the properties such as damping and stiffness in real time. And people have also come up with a hybrid system where they try to integrate two different types of vibration control strategies together. So some of the examples are where these vibration control devices have been installed in structures are shown there. So the first one is a very famous paper 101 tower. So here we have a tuned pendulum mass damper. So they have a huge pendulum which is extended to the top from the top of the building, and the motion of the pendulum tries to damp the vibration that comes onto the building due to the wind forces. So this pendulum is also equipped with some hydraulic pumps. So the job of these hydraulic pumps is in order to reduce the motion of the pendulum because it should not move too much and damage the building itself. We also have the Yokohama Landmark Tower. So this tower is also equipped with the multi-step pendulum damper. So it has three different stages. You have the outer cage, and then we have the inner cages which are suspended using a wire. And then we have the auxiliary mass in the center. So one of the problem with the pendulum mass damper is the motion. If it is not controlled, it can actually go and hit the building and cause the damage to the building. Just like we use the hydraulic pump in KPI 101. However, here they are using a feed drive mechanism in order to control the motion of this auxiliary mass. Nowadays, we are also seeing twin towers coming up, and these towers are often connected with some bridge. So these bridges are also, because of the wind forces, these towers may move slightly in, and these connecting bridge have to account for those motion of these towers. And here they have used an active control bridge where they adjust the motion of these bridges one over the other in order to reduce the effect of wind forces that comes onto the bridge. And an example of the active mass driver is the Kuwabashi building. And this building has two maximum frequencies of the period 1.13 seconds and 0.97 seconds time period of this. And in order to reduce the effect of these vibration, two different active mass drivers are used. So these active mass drivers are having a control system on their own, and based on how the building is reacting, it decides how much force it needs to apply in order to reduce the motion of the building for that particular move. So here is an example of an active mass driver. So you can see that it's a moving platform, and there is a frame. On top of that, they have put an active mass driver. And once the driver is locked, you will see how it moves. So you can see that near the natural frequency of this frame, how the structure is moving when your active mass driver is not functioning. Right now, what he'll try to do is he'll try to activate the active mass driver, and then we will see that how the response of my building is reduced because of the motion of this active mass driver. You can see now my active mass driver is moving and it is trying to counteract the forces that are coming onto the building. So basically, it is trying to dissipate the energy that comes to my primary structure into the motion of this mass driver. So let's see the control design process. So when we go for vibration control, it has three different parts. One is the system model. So we need to know what is our primary structure and do we really have an accurate model of the primary structure? Because even when we are tuning, we are designing passive control strategy, we need to know, have some idea in the frequency range that we want to work with. The second part is the measurement and estimation. Whether we can, what kind of measurement can we take from the structure, or what are the states that can be estimated based on the knowledge we have about the structure. So this also depends upon the structure information that we have. And finally, if we're going for an active control system, we need to have a proper control algorithm, which means that this control algorithm is going to decide how much control input needs to be sent to an actuator to apply the counteracting force based on the sensor information, which is the response of a structure. Right? So the typical active vibration control system looks like this. So here, let's just break it down. So we have the external excitation that can be measured using a sensor, or it acts directly onto our structure. And when a structure is there, it has some structural response. That response also can be measured using a sensor. Now, the information about the external excitation and the structural response can be sent to the control algorithm, which basically computes what is the control force that needs to be applied. So once we have that information, that is sent to the actuator, and actuator then applies that control force onto the structure. So if I have to represent that in the form of a typical control structure interaction problem, here we have the primary system, which consists of actuator, structure, and a sensor. And W is our external excitation that acts onto my system. Z is the variable, basically the response of a building, which we try to minimize. It can either be acceleration or a displacement based on the requirements. And then we need, using the sensor, we measure certain response variables. So those response variables are called as the Y. So now these response variables are the voltage signals. So these are again converted into a digital, analog to digital converter, and sent back to a control computer, which has a control algorithm. Now, this control algorithm decides what are the forces that needs to be, control forces that needs to be applied onto a structure. They are again converted back from digital to analog and sent to our actuator. And mu is called as the control of the actuator. So even in controls, we have two different kind of strategies. One is called as the feedback strategy, and other is called as the feed forward strategy. So feedback, as the name suggests, what we try to do is we try to see how my structure is responding, and I use that information in order to decide my control input. The second one is the feed forward strategy. So what happens in feed forward strategies, we measure the disturbance itself, and use that information to design my control forces. So in the feedback, it can adjust for any errors that takes place, and some of the methods that are feedback that uses the feedback control mechanisms are linear quadratic Gaussian controller, H infinity controller, or some adaptive filtering methods such as index elements. So the advantage of these feedback controllers is that they're very simple to design, and we really don't need a model of our system, which is shown here by GFS, in order to design these controls. And they have guaranteed stability when they are acting as a collocated system. The disadvantage is that it can only correct after it has sensed that some error has happened, and it has to take input from sensor, and it can work only on limited bandwidths. So there is only a particular frequency range for which the feedback control can work. The feed forward is it can anticipate and correct the errors before they happen. That is the advantage of that. Uh, in this also no model is required, and it can work over a wider bandwidth, and it can only work where we have a good type of sensor which can measure the input disturbances. It will disadvantage is that it requires a reference signal, and response may be amplified in certain part of systems. So based on the type of sensors that are available and based on the quantities that we can measure, we can actually decide whether we want to go for the feed forward control or the feedback control. Or we can also go for a hybrid control which uses both feed forward and feed forward feedback. So an example of the feed forward control is again a car system. Let's say I have an engine, and most of the engines are now car systems are now coming with the active noise cancellation, which is also there in various headphones nowadays. So what we do is we have the sensors that are inbuilt into the car, which tries to sense the noise which is coming from the woofer or due to the engine of the car, and it detects those cars and it tries to generate a signal which cancels this effect. It's basically a destructive interference. So it tries to generate a signal which is opposite to that, and because of which it reduces the sound that is experienced by the rider inside the car. So let's say if I have to go for a feedback control, so here the simple case is shown for a single degree of freedom system. Here the actuator is the active part of my structure. So we have the base motion, and then we have attached an accelerometer to the structure. We measure the acceleration of the structure, and we design a controller such that it designs what force needs to be applied in order to reduce the motion of this particular mass. So let's say if I want to increase the damping into the structure, what I can do is my controller will simply be an integrator of the acceleration, because we all know that integration of acceleration is a velocity, and the velocity dependent force is basically corresponds to the damping. So if I use my controller as a simple integrator, it will work as an active damping for my system. So in SCRC also we have worked on various kinds of energy absorbing devices, which are shown here. The first one shown is the X-plate passive energy dissipating devices. Then we have the X-plate yielding dampers. We have also worked on the development of indigenous base isolation system with the various agencies such as Indian Rubber Board, and some of the magnetoradiological devices, which will be covered in the next tomorrow's lecture by one of my colleagues. So these the efficacy of these different methods have been tested for various structures by a series of numerical experiments, as well as some shape table testing. And if you want more information, you can refer our website for these energy devices. And various design charts were also provided in order to facilitate their integration into the structure by the design. So now let's come to the part 3 of my presentation. So here we will focus upon different cases where whatever we have covered till now will be the knowledge about that will be applied. So the first case that I'm taking up is called as a active mass driver. So here we'll just see how we can implement this in the MATLAB. So this is an example problem which is already provided on the MATLAB, and we'll see how can we do that. So here we have a 7-story building, and on the top of the 7th story, we have an active mass driver. This active mass driver system consists of an actuator, and we have a sensor which basically measures the response of the top story. It uses that, and then we have a control algorithm which is defined by H of S, which determines what is the control input that needs to go to this actuator in order to reduce the motion of this top story of the building when it is subjected to some seismic disturbance. So the main objective for us here is how do we design this H of S, which is the controls for this active mass driver. So here you can see that the actual experiment that was carried out, and then we have the model here and the different states of the structure. So we have the displacements here, we have the velocities, we also have the acceleration of our control driver, which is the active mass driver, and also the acceleration for that. And the input to the system is the ground acceleration, and control input that goes to the actuator is given by U. So to start off, first we need to model the earthquake. Either you can directly use the earthquake time history for a particular earthquake if you have, otherwise you can model a filter which is shown here. So here you can see that the filter transfer function first we evaluate, which is stored in the variable f. And once we have the filter transfer function, we can pass a white noise to that in order to arrive at a particular time history. So here you can see that we are appending that filter to our main plant. So here the structure that we want to control in is called as the plant in the control theory. So we append this external disturbance, which is in the form of an earthquake, to our plant. And you can see here we are basically showing the response in terms of the drifts and the acceleration of a structure where we do not have any vibration control. So this will serve as a benchmark for us in order to compare the response of an uncontrolled structure with the controlled one. So next is we have to design this control. So we need to define our objective for that. So these objectives are defined in terms of either soft constraints or the hard constraints. So that you can define in terms of a tuning goals. So soft constraint basically tells that, okay, you need to minimize this. It does not put any hard constraint or a value onto that. So here we are trying to minimize the displacement and the acceleration of these three stories. And we also have some hard constraint, which can be in terms of the control efforts, because we have to limit the displacement of our mass. So you cannot have indefinite displacement for your active mass driver. It is limited. So, and also the force, the acceleration level that it can achieve may also be limited. So those we can define in terms of hard constraint. So once you define your constraints, you can use system command in order to design a controls for your controller structure control system. So you just need to use one command here in order to design control. So you can see how much it is simplified. So all these optimization happens in the background. All you need to do is just define what are your constraints for the problem, what are the variables that you're trying to minimize, and what are the hard constraints, and give the structure of your plant, which is basically the model of your building, and it will automatically tune the controller for you. And then you can compare the performance of your control and the uncontrolled structure. So here you can see that how the standard deviation for responses for your displacements and acceleration has come down because of this active mass driving. And you can also plot the time domain response for the earthquake chemistry that you have generated using that filter, using an LSIM command. And here you can see how the interstory drifts had reduced because of the use of your active mass driver. So the blue one is the open loop, which basically means that you do not have the active control system acting onto the system. And red one is the closed loop, which means when your control becomes active. So similarly, you can do the same exercise for the acceleration as well. So overall, you can see that the controller is able to bring in the reduction in terms of the drifts and the acceleration of your stories while meeting all the constraints that we have defined for our system. So for your particular actuator that your mass driver that is available with you, you may have a different constraints. All you need to do is enter them correctly here, and you can design and control algorithm for your active mass driver. So coming to the second part of the case study, the second case study I'm going to take is the hybrid testing of a shear building model. So here we'll try to use the hybrid testing and see if we can evaluate the response of a 2-degree of freedom system just by testing only a part of it. So here you'll see that my emulated system is basically two masses, M1 and M2. It's a 2-degree of freedom system. But what I'm doing is I'm testing only M1 physically. So the M1 is represented using this shaker and the frame assembly. So the bottom part of the structure is physically tested, and then we place a shaker on top of it. So here we are using an electrodynamic shaker as a transfer system, and we will operate this shaker in a way such that it applies the same reaction force that will come because of the mass too, which is there onto my base structure. So in order to implement the hybrid system, we need some experimental setup. So that experimental setup is shown here. Here you can see that we have a signal conditioner. So basically we have an acceleration sensor that is mounted onto my mass one. in order to see how it is moving. So that again I take through my signal conditioner and feeds it back to my D space. So D space is basically the main part of this hybrid testing, which is implementing our control algorithm. So whatever control algorithm we design in our PC is downloaded onto the D space, and D space is basically taking the feedback from my structure and doing the calculation and deciding how my shaker should move. And that information is again sent back to the amplifier for the shaker, which drives this shaker. So as I shown earlier, the conventional way of doing this hybrid testing was tracking, which means that they design a controller such that it tries to negate the effect of all these extra dynamics in the form of natural physical feedback sensor and transfer system that we have introduced. It should be able to cancel the effect of that. However, we try to take a slightly different approach. I'll quickly explain why. So when we go for this tracking, what we are basically asking is our shaker to be mechanically steered. So which means like I give a certain displacement command to the actuator, it should exactly go and apply that. So which means this is acting like a very stiff system. Now this stiff system approach may not always work because my physical substructure to which my actuator is attached is actually having some dynamic properties. It has some resonances. So when the actuator is trying to act like a stiff system, when it encounters the resonance of my physical substructure, it may not be able to maintain that displacement requirement or the force requirement. And another thing is it works only for a small range of frequency. It cannot work for a wide range of frequency. It will also require, if there is an inaccurate tracking and time delays, you need a additional compensation mechanism for that. And also you need specially designed time integration scheme with the dissipative characteristics in order to prevent your system from getting unstable. In order to circumvent these disadvantages, we adopted impedance matching approach. So what happens in impedance matching is instead of seeing actuator or shaker as an additional system, we see that as another dynamic system. So basically we try to design a controller which basically mimics the behavior of my virtual substructure. So here you see that I have the virtual substructure here, but in the second control loop, I have a controller and a transfer system. So all I'm trying to do here is make sure that the dynamics of my actuator are as close as possible to my virtual substructure. So in order to show in a very simple form, let's say I have a physical substructure which I'm testing, and then I have a virtual substructure. So this is just structure whose response I would like to evaluate for a ground motion. But when I go to the hybrid system, I do not have a virtual substructure. I replace that with a shaker. So that is called as the TS layer. So all I need to do here is design a control input to this shaker such that it mimics the behavior of virtual substructure. So once we do that, we are not really asking our actuator to act like a stiff system because it has its own dynamics. It may not follow all the time. The second thing is we are actually decoupling the control design procedure from the physical substructure. So physical substructure is usually the part about which we do not have much information, and that's why we are actually testing that. Since we only want our actuator and controller to behave just like my computer model, I can validate that even without coupling it with the physical substructure. Another advantage of this approach is that even before connecting it to the physical substructure, I can actually find out the feasible application before the experiment. And we do not need any special time integration scheme, and we can validate the controller without physical substructure. So these are some of the advantages if we go for impedance matching based approach for control design for hybrid testing. So we did a numerical investigation for different kind of virtual substructures. So we wanted the shaker to replicate the behavior of a single degree of freedom system, multi-degree of freedom system, and also a non-linear SDF hysteretic system. And we also tested, let's say I have a base excitation external input. There can be a case where we have the excitation coming into my virtual substructure, which can be in the terms of force. So those cases also be validated. So we have extensively tested this impedance matching methodology for different kind of substructures and different kind of force scenarios. So the properties were chosen such that the resonance frequencies are greater than 5 hertz, because in order to ensure that the acceleration sensor is sensing these frequencies correctly. So there were different methods to design. The first and the simple method is you just equate the transfer function of my virtual substructure to that of the shaker, and you get a controller for that. So here I have shown what is the controller that we got. It is just by simply equating the transfer function, and it is called as a naive inversion method. So here you can see the comparison of our TS is the shaker, BS is the computer model, how well it is matching for all the cases. Then we have the another way to do is, instead of directly equating, you can actually use some kind of optimization. So what I try to tell is, okay, I do not know whether you actuator will be able to reach the exact dynamics of the virtual substructure. All I want is to come as close as possible. So in such cases, we can go for the optimization. The advantage of optimization is that you can add additional constraints. So if you have any physical constraints in terms of hard constraints, those can be added while evaluating the controller for your hybrid test. And then this is the limits on the control. So I can actually formulate this as a multi-objective problem and tell, okay, I don't want my shaker to move too much. So it will not be able to exactly match, but it will still try to replicate the behavior of my virtual substructure. So here you can see, if I restrict the motion of my shaker too much, it is not really able to capture the resonance of my virtual substructure. But as I start relaxing that, it is able to capture accurately the resonances of my virtual substructure. So there is a trade-off between the control effort that you want to put in and the kind of accuracy that you want from your system. So after designing the controller, we validated these controllers without first integrating it with the physical substructure. So here the controller alone is validated. We subjected the shaker alone to a base motion, and we saw whether it is able to replicate the dynamics of the PS or not. So here you can see, for all the three cases, it was found to accurately capture the dynamics. And once we validated the controller, so this was controller designed using a naive inversion approach, which is equating the transfer function. These are the controller designed based on optimization, and this is with the limits on control. So the behavior that we expected numerically was simulated during the experiments. And once we validated the control, so on the left side, I've shown the setup for the validation of controller without my frame. And then we actually have the frame here where we validate the controls with the help of a shear building model. So now we integrate our shaker with the first story, and we try to see now whether, if I design my controllers for a single degree of freedom system, whether with the frame I'm able to get the 2 peaks or not, because it is supposed to behave like a 2 degree of freedom system. So some of the features of our physical substructure was, we chose a very lightly damped PS because the controls becomes very difficult when you have a lightly damped physical specimen. So we choose a very lightly damped structure, and then we design the controllers for each of the case and see whether we are able to get the response of full system. So here you can see that we have tried the virtual substructure for the different stiffness values, and for each of them we were able to get 2 peaks, which means ideally my hybrid system is behaving like a 2 degree of freedom system, even though I'm testing only frame, bottom story. So similar thing we did for when the excitation is at the base, when the excitation is at the top. And for both the cases, we were able to capture the response of the complete system. So the third part of my case study is on the thermomechanical RTHs. So you have seen a very simple case where we have a building and 2 external excitation, but let's say I have a very complex loading condition where I have the thermal forces as well as the mechanical forces, whether I can use hybrid testing there. So what we did is it can also be used called as a multi-hazard hybrid testing, where where you have the wind and you have the earthquake, and one part of the loading of the structure, let's say wind, is applied numerically, while the earthquake is applied using a physical test. So in the thermomechanical testing, what we did, we took a case of a base isolated structure and we have a superstructure on top of that. And we all know that these elastomeric isolation systems are designed with the nominal properties. And we also know for a fact that when there are environmental variation in terms of the temperature, the properties of the elastomer may change. And if the properties of your elastomer changes, it may detune your isolation system, and it may not be as effective as you expect it to be when you designed it with the nominal properties. So the whole aim of this exercise was to see how this temperature variation are actually affecting the performance of my isolation system. So in order to do that, we took the elastomeric isolation system. We had to have a control system in order to change the temperature around this isolation system. For that, we used air heater and a thermal controller. So with this thermal controller, we can actually tune the surrounding temperature around this isolation system. And then in order to simulate the superstructure dynamics, we replace that using a shaker. So this shaker again tries to replicate the behavior of different superstructure. And then for different temperatures, we try to see whether the response of my complete system is changing when I change the temperature or not, and how much is it changing. So you can see that some kind of loading which is as complex as this one, you can utilize this to get the response, thermomechanical response of your isolation system. So here you can see that first we started testing. First we wanted to see whether the isolation properties are changing at different temperatures. And here you can see the frequency response. As we increase the temperature, my isolation becomes softer, due to which we have seen a decrease in the natural frequency of the system. And here you can see the response of the structure at two different temperature and also the time domain response. So you can see that if you use the nominal properties of your isolation system, you may not be able to accurately predict the response. So when you are designing this isolation system, these temperature variations should also be accounted in some way in order to make sure that it does not destabilize, detune your system too much, and it ensures minimum performance that is required from your isolation system under the environmental variations. So the fourth case study that I want to take is the multi-hazard RTHS. So here we are taking a case of, again, the wind turbine, which spans across multiple domains. So we worked on the vibration control of this floating offshore wind turbine. So floating offshore wind turbine, in this particular case, we have a tuned mass damper, which is installed in the nacelle of my wind turbine. So the testing of such kind of a system becomes complex because you have to scale down your wind turbine model. The height of the normal wind turbine for this particular case was 90 meters. And once you scale down, you have to scale down your TMD as well. So it becomes difficult to validate that because physically realize that reduced scale becomes impossible. So what we have done here is we have taken a prototype structure which represents a tower nacelle assembly, and then we have placed a shaker inside the nacelle. So the job of this shaker is to simulate the behavior of the tuned mass damper and apply that reaction force onto the tower, as well as it has to apply the wind loads that comes onto the structure. So you will see here the virtual substructure for us is the TMD and the wind loads, while my physical substructure is the tower nacelle assembly. So the control system looks like this. So here we have a virtual system which in the form of a TMD, and it applies, gets the reaction force. That reaction force is applied by the shaker onto my prototype tower. And then we have a sensor which measures the acceleration of my nacelle, and based on the control algorithm, it decides what control input should go to my shaker so that it behaves like a TMD. So the optimization problem so here first we need to design the TMD itself. So even to design the TMD, we use the optimization problem, or we can use the analytically available solutions as well. So the optimization problem in simplified terms can be written like this. So minimize the transfer function. So this transfer function basically tells for a given input what is the acceleration or the displacement of my nacelle. And subject to, we have some constraint because we don't want the stiffness and damping to reach some unrealistic values. So we put some constraints on that. So under these constraints, we try to find out, we fix up a mass ratio is usually fixed. So in this case, it was fixed as 5%. So based on this, we try to evaluate the mass stiffness and damping for our tuned mass damper. So once we have that, then we design controls for our headwind test. So here you can see the experiments that we have carried out, and here the performance is compared in time domain as well as the frequency domain. So here you can see in frequency domain, without the tuned mass damper active, we have a resonance around 16, 17 hertz. And once I introduce my tuned mass damper, I'm able to bring it down, which is expected from my design optimal TMD. So you can use this methodology to basically experimentally validate your optimally designed TMD, and you don't have to really manufacture a TMD because let's say you evaluated certain K and C to physically realize that may be difficult, and you may have a differently tuned optimal dampers, 4 or 5 dampers that you want to test. So you don't have to physically make them. You can just use this shaker to simulate the effect, the behavior of different types of tuned mass dampers, and see whether it is able to reduce the response of your structure or not. So on the right hand side, this is a time domain response. You can see a 3 reduction in the time domain response as well. So finally, I'll conclude my talk. And here we have seen that this lecture basically covered what are the different kind of conventional dynamic testing methods and what are the new testing methods. Then the second part, we covered the vibration control of structures and different strategies which are usually adopted, active and passive. And finally, we took up some case studies, and we have seen how we can use those new dynamic testing methods and new vibration control devices and how we can design them for a particular application. The first one was on the vibration control using active mass driver, and we have seen that for a 3-story structure, how we can design that particular mass driver and the controls for that in MATLAB. And then we took 3 examples of the hybrid testing where we have got the response of a shear building model, a thermomechanical response of elastic cancellation system, and the validation of a TMD for a wind turbine. So these are some of our publications. If you want to have a more closer look at the things that were presented in this lecture, you may kindly refer these for further details, or you can. Thank you for your kind attention, and this concludes my talk. And if you have any questions, I'll be happy to answer.